So good evening everyone. So today we are taking this extra lecture. So it is based on this design of photovoltaic system only. And I am Ravi Kumar, a PMRF research scholar at IIT Bombay. So let's start this special lecture. So first of all, if we have a PV module in field, so we require its maximum power point and all. So how do we characterize it? If we have PV module in practical, how can we get the maximum power point? How can we get the IV curve and all? So for this purpose, if we have, let's say this is a PV module. So we will connect a variable resistor here, and then we will measure the current and voltage. Even this ammeter you can have one more resistance here, and you can have voltage, and then I will be equals to V by R. Even from here you can get this I as well, and across this variable resistor you can get the voltage. So this is the simplest way. Now what will you do? This is a rheostat variable resistor. You will change this and you will find different points and you will plot like this. It's V, it's I. If you are like changing it from 0 to some 10k ohm value, let's say. So at 0 resistance, the current will be maximum, voltage will be 0. So you will get some point here that will be corresponding ISC. Then you will get some point here, here, like this. Then it will come this way. And at particular this point, this will become very high resistance, and at this condition our voltage will be maximum, that is the VOC. So this is the simplest way. If you have a PV module or PV cell, you can characterize that at your home. Even while you purchase a PV module, they always give data sheet which contains like PMPP, VOC, ISC, VMPP, IMPP, also efficiency, fill factor. So these are the terms, and some terms depending on the temperature and all. So these are the basic terms which you will get from the data sheet only. Now we will move to the sizing of a standalone PV system. So in this particular part, what we are doing, we have a home, let's say our home. We have some instrument inside our home, and we are having a, we want to put a solar PV to run this home or to supply the electricity, and it is standalone. It means no grid connection. So here grid connection is not available. That's why we are saying it is an standalone PV system. So from this picture you can see this is the schematic of a standalone PV power system, and here you can easily see we have a solar array, then we have a charge controller, we have an inverter, we have some loads, AC load, some DC load, and some battery. But what do we understand from the sizing point of view? From the sizing point of view, we understand what capacity, how much PV module we require. Battery, same, how much battery or how many batteries and what capacity. This AC load and DC loads, these are the fixed component of our home, and inverter also we see which inverter we should utilize. So these are the questions which comes from this designing piece. So why system designing or system resizing is important? Because it refers to the fitting the PV system specification to the actual requirements. So what we are doing, we are first calculating the requirements, and then we are finding the actual specification of a PV system which we require. So in this particular case, we calculate number of modules, number of batteries, how to configure modules and batteries. So our objective is to make a reliable working system, and also sometimes all the things or all the choices are not based on the calculation. Sometimes like the clouding and all. So you cannot quantify the clouding, you cannot quantify how much days you will not get the sun and all. So we need to consider each and everything. And judgment is essential because in India we have this variation in insolation from like Jammu Kashmir to Kanyakumari and from here west to east. So there is a huge variation in this insolation of solar radiation. That's why we need to consider, or we need to design a system while considering a location in our mind. So what is the significance of designing system? So sometimes we may end in designing like over designing or under designing. So let us consider one case. In this particular case, we have a PV power, like PV modules, and it is having enough generation, so it is supplying to load as well as it is supplying to battery. But sometimes what can happen, it can oversupply to battery. So here in this condition, our battery is full, then also it is also supplying more. So this is the one condition. Sometimes it may be like under designing. So in this condition, our load requirement is not satisfying with this PV system. So we are requiring additional battery, or also we may require additional diesel engine. So these are the conditions which we need to keep in mind while designing a PV system. So in this standalone system designing, what we will do, first we will do load estimation, then we will move to this radiation estimation, how much radiation and all. Then we will move to the module sizing, and then we will move to the battery size. Because this radiation estimation will like affect this module sizing, and battery sizing will depend on this load estimation. So one more important term, that is the autonomy. So we don't have any place in India where we can say like there will be no cloud or there will be sunlight each and every day without any fail. But that is not the case. Sometimes it's rainy season, sometimes it's like unexpected rain or unexpected clouds. So we need to consider some days in between at which we assume that our solar system will not work, and that is known as the autonomy. So this autonomy represents the days of low radiation. And this like if autonomy is low, it means days with the low radiation is low. But if higher is the autonomy, so there are the days which are more without any radiation. So in that condition, that will be higher in cost because we will require more batteries. So generally this is the thumb rule which we utilize. For critical application, we assume that our autonomy will be 7 to 14 days, and for non-critical application we assume 3 to 5 days. It means we are like designing our battery considering that our critical application should run 7 to 14 days without solar PV system, and for the non-critical application it should work for 3 to 5 days. So this is all about the autonomy. Now we are moving to the designing thing. So in this example, I am considering some design or some particular instrument at a particular home, and if you want to design your one, you can consider the load as per your house, or even first you can just understand from this example, and then after that you can design for your home. So in this particular example, I am taking an individual home having two fluorescent lamps of 40 watt which runs for 5 hours. So from this example you will understand how much or in what form the data you required from your house. And also along with these two fluorescent lamps of 40 watt, we have one fan of 50 watt which run for 8 hours. Then we have one TV of 50 watt that run for 5 hours. Then we have one DC lighting, that is a DC load. It is a 5 watt 12 volt system which works for 2 hours. And here we are considering it is a non-critical application, so our autonomy will be 3 to 5 days only. And place of installation we are like designing for the Surat. So the solar radiation or solar energy at Surat is given like 5.4 kilowatt hour per square meter per day. So this is a small home. We are considering these applications, these instruments or these applications at home. So first of all, we were saying we need to identify the irradiation, or we need to identify or calculate the irradiation thing. So this is the peak sun hour, or we can say the daily sun profile. It is the sunrise, low radiation time. Then it is the sunset, low evening time. But at the afternoon, or after like let's say 10 p.m., 11 p.m. till the 4 p.m., we have high radiation, and this radiation is like for the 5.5 hours. It is like yearly average. So this is the known peak time at which our system will work. So we are assuming that 5.5 hours of the sunlight our system will work in a day. So we have estimated the solar radiation. It's like the solar radiation is for 5.4 hours, or we can say 5.5 hours. Nothing will change much.
Water. Water.
Nothing will change here. So now we need to estimate the load. So first of all, you have seen that we have two types of load. These are the AC loads, and these are the DC loads. So from these AC and DC loads, how much battery we require? That we need to identify first. What is the sizing of battery which we require? So in this particular case, we have a light, we have a fan, we have a TV. The quantity of light is 2, fan is 1, TV is 1. Then we have load, that is a 40 watt. This is the 40 watt of single light, 50 watt of single TV, single item. And use of hours is already specified, that 5 hours, 8 hours and 4 hours. So if we do so, if we multiply this with this, so we can get the watt hour, because we have 50 watt which is running for 8 hours, so it will be around 400 watt hour. We have 50 watt running for 4 hours, it will be around 200 watt hour. Similarly, one will be 200, and we have two quantity, it will be 400 watt hour. So this is the way by which we can calculate the total load consumption in our home. So we have total load, that is 180 watt, and in watt hour it is 1000 watt hour. So it's all about AC load. For the DC load thing, we have 5 watt bulb which run for 2 hours, so that is a 10 watt hour, and it is running with the 12 volt battery. The specification of this bulb is 12 volt, so it is of 0.83 ampere ah per day. So what is the capacity of battery when you go to market? How they specify the capacity of battery? They say ampere hour, they say 100 ah battery, they say 180 ah battery, they say 200 ah battery. So first of all, we need to change each and every load into ah form, ampere hour form. So for the DC thing, it is like directly we have watt hour, we are dividing with the voltage, then we are getting in ampere hour. So for now DC load we already converted, we will convert this AC load into ampere hour. And also the inverter which comes, it is not like that I am getting 180 watt, so I will get the 180 watt inverter in market. So it's like that if I am getting 180 watt, so I should, if market is having 200 watt inverter or 150 watt inverter, so I will take the 200 watt inverter. So it should be always more than what you have estimated. And our system, because we have a DC load of 12 volt, so we are designing the entire system with the 12 volt DC side. So our inverter will should have an input of 12 volts. So our inverter will be of 12 volt input system. And the efficiency of inverter typically is 90%. So this is the choice of an inverter. Now there are some important points. Sizing should be based on like daily, weekly or average load. And also sizing for the worst month of the year. We should do the sizing for the worst month. It means we are considering here high autonomy. It is like very common thing. We should always design a system for the worst condition. So final result of this entire sizing should include which module, how many modules, and what configuration. Configuration means in series or parallel. How much in series and how much in parallel. Similarly for battery, how many batteries and what configuration, like in series or parallel, and which inverter. So these are the questions which, because if you will go to market, what you require, you require an solar PV module. So you should know which module you need to buy and how many module you need to buy, then in what configuration you need to connect them. For the battery thing, same, you need to know about the battery, which battery you require, and how many batteries you require, and how will you connect the batteries. Similarly, for the inverter, you should require the capacity of the inverter and the input, that's it is like 12 volt input or 24 volt input. So these are the things which we require. So whatever which we require to design or to put a system, those should be the output of our designing. Yes, that should be the output of our this designing exercise. So now we will convert, we have already converted our DC load into ampere hour. Now we will convert our AC load into ampere hour. So for this we have AC load. So this is the AC load. This is the efficiency of inverter, and this is the input DC load. So it's like that. This is an inverter. This is our DC side. This is our AC side. So if our AC side is coming to be 100 or 1000 watt hour. So this 1000 watt hour, how much ampere hour in DC side, because it is running from the battery. So we need ampere hour. So we need to know how much ampere hour from the DC side. The efficiency is 0.9 and it is of 12 volt. So what we will do, we will like divide 1000 watt hour with the 12 volt and with the efficiency. So this will be the AC plus we will have DC. So this AC thing which we have done here as well, it is coming around 92.59. And if we add this DC load, so this is the total requirement of ampere hour per day. So we are requiring 93.43 ampere hour per day. So our battery should be, let's say if battery capacity is like this, 50 ampere hour, 100 ampere hour, 150 ampere hour, or like 200 ampere hour. So our battery capacity should be more than this 93.43. So we can consider, let's say, 100 ampere hour here as well. So this will suffice our system. So this is about the load calculation in ampere hour, and based on this we have selected the battery. But before selection of a battery, there are few things like DOD. That is the how much is depth of discharge it can take. So battery which allow up to 50% DOD is called shallow cycle battery because it is giving only 50% of its capacity, and those are 80% DOD are called deep cycle battery because it is giving more, like 80% of this capacity. So PV application need deep cycle batteries because that it will like will be cheaper for us. And for batteries used in PV system, the allowable maximum DOD is 80%. More suitable for frequent discharge and charging situations, and it is based on the daily load. So here we are considering a battery which should have 80% of DOD. So now based on this, we will consider how much capacity of battery we require. So this is the autonomy. Now we were saying that autonomy are the days when our battery is not being charged, and our daily requirement was 93.43. So what we will do, we will multiply it with the autonomy. We are assuming autonomy that is the three days. It means in 3 days, if there is no solar radiation, our system should work. And if we multiply this daily capacity with this 3, then we are getting the load requirement or the ampere hour requirement of 3 days, or let's say the total requirement. But now comes to the battery. Similarly, let's say this is a battery. This is our output should be 3 into 93.43 ampere hour, and it is like total battery, but it is giving only 80% of its capacity. So we will divide it with 0.8, and there are some degradation as well and rate factor as well. So these are the values which is already like given in many literatures. So you need to utilize these values as well, and that are the rate factor, temperature deterioration, and maximum usable limit. And if you do so, then we are getting total ampere hour requirement of a battery, that is 326.84 ampere hour. It means total battery capacity which we require should be 326.84 ampere hour. Now if we have already choose a battery from the field or like from the market survey, we have obtained that there is a battery which is 6 volt 180 ampere hour. So how much batteries you require in series? Like let's say in series, what will happen? Voltage will add. So it is a 6 volt battery, and we are requiring how much batteries? We are requiring our 12 volt system, so we require at least 2 battery for the series connections. So to calculate number of batteries in series, you need to divide the voltage, system voltage divided by battery voltage. Then to identify the battery which require in the parallel, you need to divide this total battery capacity with total battery capacity which we require with the actual battery capacity which we have. So this is the actual battery capacity we have, and this is what we require. So if we do so, we get 1.81, which is corresponding to 2. So now we are requiring 2 batteries in series and 2 batteries in parallel, and the batteries we have chosen this. Even this will change if we, let's say there is a battery which is available in market, that is 400 Ah and 12 volt. So now we will require only 1 battery. Yes, Mohan, that's what I am saying. This is a particular choice. We can take any battery. What I am saying, like we can take 12-volt battery, so our series battery will be one only, and then we only require parallel. And it is, if it is 200 Ah, then we will require two battery only, and if it is like 400 Ah, then we will require one battery only. This is just to tell you through this example that if like this choice you can make based on the availability in the market. It is not like we have to put 6-volt battery only, or we have to, but here understand one thing, our system is being made like on 12-volt, so you cannot go and select a 24-volt battery, because we have a DC load which runs on this 12-volt only. So then this will not be a good choice. So we have identified that battery in series require 2, battery in parallel require 2. So how do you calculate battery in series? By system voltage divided by battery voltage. Batteries in parallel, total AH requirement divided by the battery AH. So by calculating or by using these formulas, you can calculate the requirement of a system or requirement of battery at your home. Now battery we already calculated, we have already selected, and we have identified which configuration, how much battery we need. Now we will move to the PV module. So we are in this particular example, these are the basic things. We have PV module, that is STC 1.5 1000 volt per meter square at 25 temperature. Okay, fixed voltage. Fixing of a voltage of PV module means you can go to the market and you can see what voltage of module you have. Then you can do this exercise. So before this, we will see a simplest thing. So we, similar to the battery, we can connect our PV module in parallel or series connection as well. So in parallel, current will increase, voltage will remain same. Current will become or will add up. Similarly, in series connection, our voltage will add up and current will remain constant. So these PV modules are also connected as the same, similar to the battery connections. And increasing both, then we require like modules in series and modules in parallel. So we using this, we can increase both voltage and current. So from the market survey for this example, we have selected that we have a module of 40 watt with IMP, that is the maximum power point current, 2.41 ampere, and we have already seen that our radiation is 5.4 hours per day, and module output will be then 13 Ah ampere hour. So actual module output will be what? So this is the module output. If you just do one thing, see, this is the ampere. If you will just connect this 5.4, you get this module output in ampere hour. So we are doing each and every calculation in ampere hour. So here also we have calculated this ampere hour for this module and for this 5.54 hours of sunshine, and it is coming to 13.01 ampere hour. So now actual module output will be how much, because we have some mismatch losses and all, and dust factor and all. So we consider this, and if let's say it is like 90%, 10% loss here, 10% loss here. So this is the actual output in field of a PV module. So this is the like one module output, one module actual output, right? So we already have seen that our PV module is of 12 volt. So how much module you require? Similar to the battery calibration, you will require only one. But our daily requirement is 93.43 watt. So now you will divide it watt hour. Now you will divide, oh sorry, it was ampere hour, right? So now you will divide this ampere hour, total required ampere hour, with the module ampere hour. You will get the number of module 8.86. So it cannot be 8.86, so it should be 9. So here we require 9 PV modules in parallel. 9 PV modules in parallel of 40 watt each. So from using this ampere hour thing, we have calculated the requirement of module sizing. Now we will recheck something. Recheck means we will see the PV module are enough to charge our battery, yes or no. We will do so. So we are doing battery recheck. So daily discharge of battery we will find out. So it is like that. We have two batteries in parallel. Battery capacity is 180, and this is the daily load which we require. And if we divide this daily load with this actual battery load, we are getting it is 25.95%, which is less than 80%. Yes, so it is right. It should be less than 80% because 80% is the DOD. And also maximum rate of charge means how many hours it will take to charge. So it should be more than 5 hours, because if it is less than 5 hours, what will happen? Our battery will become overcharged. So for this we have number of batteries in parallel into battery capacity divided by number of modules in parallel divided by current. Because it is in ampere hour and we are dividing with ampere, so we will get R. So this ampere hour with this current we can get in this hour. So it means in 16 hours our battery will be full, let's say. We are doing so because it should be more than 5 hours, because in 5 hours are the 5.4 hours are the sunshine hours of one day. So yes, our checks are satisfied here. So our system or our battery capacity or PV module capacity are right. So now we will see the final layout what we have obtained. So we have modules 1 in series, 9 in parallel, 40 watt module. Batteries 2 in series, 2 in parallel, 180 ampere hour, 6 volt battery. So this is the final layout. So similarly we will see here. So this is the ampere hour per day which we are getting from sun. This is the ampere hour per day which we are getting from PV module. This is the ampere hour per day which are consumed by this DC load. This is the ampere hour per day which is utilized by this inverter and given to this AC load. And this is the ampere hour per day which is being given to this battery. So this is the final layout. So this is the designing of a PV system for particular this example. Similarly, you can design for your home or you can design for any place wherever you want. Other than that, so yes, here you can see this is the charge controller. So what are the basics of charge controller? It blocks reverse current because battery is a source. It can give the reverse current. It prevents battery overcharge, over discharge, protect from electrical overload, and display battery status and flow of charge. This is all about the charge controller we have. But this tilt angle we have already studied in this lecture only, because it based on this tilt angle it affects the energy incident on solar PV module surface. So this tilt angle is very important. which we have already covered. Yes. So from this exercise, or we have a simple thumb rule. If there is 4 to 6 kilowatt hour energy per square meter per day, then we will only able to generate 3 to 5 units per day. This 3 to 5 unit means 3 kilowatt hour to 5 kilowatt hour. This is a thumb rule. Like from the basic, without doing any calculation, you can say these things. So battery requirement should be approximately 1.5 times of the load demand inclusive of autonomy days. Area required should be up to 8 square meter module area, up to 10 square meter with shadow effect. So these are the thumb rule. It is not important for us because we are doing actual calculation. So this was all about the designing. Now we will see different types of solar power plants which we have. So we have like grid connected, off grid, hybrid, and PV based utility. In grid connected, we have without battery large scale production, with battery small grid concepts. For this off grid PV system, which we have with battery and without battery. Hybrid, we have with hybrid means we are having other power source as well, that is like wind or PV diesel engine or another components. PV based utility means for particular application like solar lamp, solar mobile charger, or we can say solar water pump. So these are the PV based utilities based power systems. And these are the examples of like off grid, then grid connected. These are only to show you an on grid. And this is the hybrid layout. In hybrid layout, which we have one source, other source, and in between we have battery. So these are the sources, this is the storage, and these are the load. So this is a layout of a hybrid design. Similarly, hybrid design is visible here. So this is a source, this is a source, this is a source. It means we are having multiple source at a time. Let's say it work in daytime, it work in night time, or let's say when nothing, not solar, not wind, then this diesel engine will work. So this hybrid systems ensure 24/7 our energy requirement. Okay, now we will see some tools which we have, which yes, tools and equipments which we use for solar installations. So first of all, we need to like identify the inclination and all. So for this we have inclinometer. So this is an angle measurement device which measures the angle, because while putting a PV module at a particular tilt angle, which we need to measure the angle. So usually we utilize this device to check the angle. Then we have compass. It just tells us about the direction, where should be the like sunrise, sunset, the entire from which direction the sun will be in afternoon and all. So using this we can identify at a particular place. Then for the shadow analysis we have the shade tool. It tells us about the shading or the energy loss due to shadow. Then we have PV module testing equipment. So see, if PV modules are being like fabricated at a particular industry, so those are not tested in the actual environment. Those are tested under these laboratory scale items, or we can say the module simulators. So these are used to identify or to characterize this PV module after the production. Then we have for the current, voltage, resistance and continuity measurement, multimeter, kilometer. Then we have PV analyzer in field. What I was talking about, that by changing the resistance, you can measure the IV curve of a PV module. So that same thing you can do with this PV analyzer as well. So it gives you IV and PV measurement of a PV module. Then we have insulation tester. So it is used to measure the insulation between the different layers of a PV module. Then we have a very specific device, that is the pyranometer, and this pyranometer is used to measure the global radiation. Or sometimes if we shade it with some time, and it can measure the like diffuse radiation. And there is a relation between this global and diffuse. You can then find out the beam radiation. These are the different types of radiations which you can measure using this parameter. Then to find the wind velocity, we have an anemometer, and these are the like tools which are used to connect the cables and all. Okay, so nowadays what is going on? So there are some new innovation in the field of solar PV power plants. So you can see we have PV power plants on a canal. So like we are utilizing this space, and also this water which is going in like below this PV power plants. This is giving a cooling effect to these PV systems, and this cooling effect is like maintaining the efficiency of these power plants or PV modules. Then similarly, we have these PV modules on water here, here, yes. Also like PV modules on railway stations, you can see here. These are the like arrow. This is the some aeroplane. This is a like boat in water. This is a car, or we can say vehicle on road. So these are the new trends which are coming in this field of solar PV applications. Okay, so that's all about today. So using this particular thing, like I will upload this video, similarly following those rules, you can measure or you can identify the load requirement at your home. Then you can find out the battery requirement, then you find out the PV module requirement. So it is not a rocket science. So using these entire thing, you can design a PV system for your home. And I will suggest you, if you have your own home and if you are not having a solar PV system at your home, then you can have it. And government is also having some kind of subsidy nowadays. You can apply for that. You will get some subsidy as well, and you can have your own solar PV power plant at your home. Okay, Mohan was asking some about this like design and all. I could not like connect with those people, so you can. I will send you something later on if I will get there. Even you can write an email to me, so it will give me a reminder. Okay, so this is my email ID as well. Whenever if you require any help or if you require having any question, you can contact me. So this is the last lecture which we are having. I hope you learned something about the solar PV system and all, and like read from different places if you have any doubt. There are so many resources available on the internet. Thank you, Mohan. Hopefully, we will connect in future as well for more courses. I'll take more courses on solar PV. Bye. Thank you, everyone. Have a great day. Happy learning.